I would like to thank the organizers for giving me the opportunity to give this talk. And I would like to give in this talk some remarks on equivalence problem of graph-to-graph transducers, which are results of joint work with Mikołaj Bojańczyk. Transducers are automata that transform combinatorial objects. And those ideas have been researched since 1960s. From that time, there has been many transducer models that have been introduced. For example, ones that transform strings into strings, or ones that transform trees into trees. But also other combinations and other combinatorial objects can be used. Let me just mention transformations that map tree to strings. And each of these types has got many of the models, like tree-to-tree transductions are, for example, macro tree transducers, or streaming tree transducers, or deterministic top-down transducers, etc. Equivalence problem asks, given two transducers, T1, T2, from a certain class, let's say streaming tree transducers. Given T1, T2 streaming tree transducers, decide if they are equivalent in a sense that they define the same function. So in other words, for every input, both T1 and T2 return the same output. So in particular, domains where T1 and T2 are defined have to be the same. Important classes of transductions, such as streaming string transducers or streaming tree transducers, can be defined using both logic and automata. So logical description is a high-level description that lets one define transformations a little bit like in the natural language. And automata, on the other hand, are a low-level description that can be tested algorithmically, for example, for equivalence. In this talk, we will be approaching a problem of equivalence of graph-to-graph transformations which are defined using logic. First such transformations defined this way explicitly or a bit explicitly, a bit implicitly, date back to year about 1990. Examples of graph-to-graph transductions that are defined in monadic second-order logic, which we call shortly MSO logic, or just MSO, are, for example, this one. A transformation that, in a graph, subdivides every edge. So it introduces a middle point in the edge. It is a deterministic transduction. However, we will not either define what deterministic means or prove that it is deterministic. But it is a remark that it is deterministic as opposed to another example, which is non-deterministic. And it is defined shortly, disconnect a cycle. So this transduction takes a graph, checks if it is a cycle, and if it is, it returns a path which has the same number of vertices, but a path that has the same number of vertices. And it cannot be defined by a deterministic MSO transduction, intuitively speaking, because this is because there are two endpoints. The endpoints are distinguished somehow, and that would imply that there are some distinguished vertices in the input. But however, in the cycle, there are no distinguished vertices. this reasoning could be made precise to prove that this transformation cannot be defined by a deterministic MSO transduction. It, however, can be done non-deterministically, and again, just on the intuitive level of description, it is done by non-deterministically choosing an edge which will be removed. There is a phenomenon in the transductions that if the output structures are the same, let's say trees, this will be the example. If we allow more automorphisms, or even more general, more ways to describe an output object, then the more difficult it is to decide equivalence. This is not made precise, and it is true to only some extent, but still there is a very concrete example where we can show this. Let's investigate MSO tree-to-tree transductions, and let's see three kinds of trees that can be outputted. It can be rooted ordered, rooted unordered, or unrooted trees, where rooted unordered do not have an order on the siblings, and unrooted are just graphs, no root, just graphs that happen to be trees. Now, rooted ordered can be reduced to rooted unordered via an injective MSO transduction, and the same holds in the second case. What is remarkable that there is no transduction back. Rooted unordered cannot be reduced to rooted ordered via an MSO injective transduction. The same holds for the unrooted to rooted unordered. So this is the first reason why the difficulty strictly rises here. And it is also reflected by the time when MSO transductions where equivalence of those MSO transductions was answered, if it is decidable or not. For rooted ordered trees, in 2005, it was proven that equivalence is decidable. Equivalence is also decidable for tree to rooted unordered tree MSO transductions. However, it has been proved just 2 years ago, 13 years later than the rooted ordered case. An unrooted case is still open. We do not know if equivalence is decidable or not. And in this talk, we will be trying to answer the question for graphs. So, unrooted trees are a special case of graphs. This is a case where the tree width equals 1, and we will not define tree width, but this notion will play a role in the slide after the next slide. The main results that we got are, there are two main results. The first one is that we introduce an automaton model for graph-to-graph MSO transductions of graphs of banded tree width. And it might seem that it is some limitation, but that the tree width is banded. But for the other case, we already have an answer, and equivalence is undecidable. So this is the only case that is left, and the only case where potentially equivalence might be decidable. The second result that we got is decidability of equivalence of such transductions up to an equivalence relation on output graphs which is having the same number of walks. Let's look at the following example. If there would be transduction T1 and T2, and transduction T1 on some input would return the left graph, and on the same input, transduction T2 would return the graph on the right. Then they would be considered equivalent, because both graphs have same numbers of walks for each length, namely 7 walks of length 0, which are just vertices, 12 walks of length 1, which are just pairs of vertices connected by an edge, so 2 times the number of edges, because the graph is undirected. There's 24 walks of length 2, because, for example, in the graph on the right, the isolated vertex does not admit any walk of length of positive length, so even 1 or 2. However, each of the 6 vertices admits 4 walks of length 2, because you can either go right, 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 left, 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 or left, right. Unfortunately, we can decide if transductions output graphs equivalent up to relation which identifies, well, very different graphs. Those 2 graphs in the picture are not that similar, and yet they are identified. The idea of the proof that we are exploring is that combinatorial objects, in our case graphs, sometimes can be encoded into algebraic objects like numbers or polynomials or power series. And it is important that this encoding should be compatible with composition of output objects. So if transductions output trees, then those algebraic objects should be compatible with the operation of joining the trees along the route. Let's go straight to the examples. Strings, which are composed by concatenation operation, can be mapped to following pair of numbers. 19 here stands for the number which is represented by ABBA when A stands for 1 and B stands for 0. So as a binary number, this is 19, and 2 to the power of 5, 5 is the length of this number, is 32. So each string can be mapped to such a pair of numbers, and this is an injective encoding. It is compatible with concatenation, and this innocent-looking encoding allows to use algebraic geometry techniques, algebraic geometry theorems like Hilbert's basis theorem, also computational algebraic geometry algorithms like testing inclusion of ideals. So this encoding has been used, for example, in 1999 for proving decidability of equivalence of deterministic push-down transducers, and also in year 2000 for proving decidability of equivalence of HDT0L sequences. Let us move to another example. Rooted ordered trees can be encoded as strings, so we do not cover them here, because they already are covered by the first example. Now, on the other hand, rooted unordered trees can be encoded also by algebraic objects, namely by polynomials. And this idea has been used in 2018 to prove decidability of equivalence of MSO transductions from trees to unordered trees. And what else can we say? Next, let's see what happens to graphs. If we only could find an algebraic object that graphs can be mapped to, and that this encoding is injective, then we would be able to decide equivalence for graph-to-graph MSO transductions of bounded tree width. This method cannot prove undecidability. It can be only used to prove decidability of equivalence. So when we are interested in walk equivalence, then what we use is a walk power series. by power series we mean such infinite polynomials, and here the numbers of walks on the graphs that were on the previous slide are encoded in such a power series in the following way. The number 7 stands for 7 walks of length 0. That's why 7 times x to the 0th power. 12x stands for 12 walks of length 1. 24 times x to the power 2 stands for 24 walks of length 2, and so on. So such power series can encode numbers of walks of each length. And actually this idea is not new. It is very classical in algebraic graph theory to count certain substructures, to count certain patterns using power series. And why are they useful? For example, they can be written concisely by a rational expression like this. And just a remark is that the power series that can describe walks are always rational power series, and these are the same up to some transformation. They can be transformed to weighted automata and vice versa. And therefore it's a fun fact that therefore we have automata that output power series, so we have automata that output automata. But going back to the problem, is there any power series that can describe a graph up to isomorphism? We made a study on the literature on graph polynomials, and there's many of them, and they are used for counting lots of substructures, lots of patterns in the graphs. However, it was not very helpful. There are two polynomials, at least we encountered two polynomials that were used the most. Tat polynomial, which generalizes many other polynomials, like matching polynomial or chromatic polynomial. And unfortunately, it does not distinguish any trees. And characteristic polynomial, on the other hand, distinguishes some trees of given size. However, in the sense of probability, it does not distinguish them almost surely. So it can be used and it will contribute something to equivalence. However, in the sense of probability, all trees are the same, have the same characteristic polynomial. And so the question is there some polynomial which distinguishes all trees and is compatible with composition of trees? Or, even better, the polynomial that has this property for all graphs. Now I would like to say something positive and something negative on the approach that we have. And the same fact will be positive and negative. It happens that on trees, isomorphism, being isomorphic, is the same as not being distinguished by Weisfeiler-Lehmann isomorphism test, also called color refinement algorithm, which relies on counting how many vertices of certain kind there is in a graph and doing such things face by face. There's also a result which says that being isomorphic is the same as having same numbers of homomorphisms from trees, which are the same things. Those homomorphisms from trees are the same things as branching walks. So what is positive about this result in our case? We are able to count walks that have trivial branching. So we are able to count some walks. Therefore we can do this thing partially. On the other hand, we were trying to find appropriate algebraic objects to count branching walks, but with no success, and it seemed that the problem is very challenging. This result is generalized to tree-width k graphs. We will not define tree-width k, tree-width notion. It is some notion of similarity, and number k says very, like on the intuitive level, how similar a graph is to a tree. So on such class of graphs, isomorphism is the same as not being distinguished by k-dimensional Weiss-Feitel-Lehmann algorithm, which also relies on counting certain patterns. And also it's the same as counting, as having same numbers of homomorphisms from graphs of tree-width k. So this is positive that there are results that describe isomorphism by means of counting patterns. And counting patterns is a broadly studied area in algebraic graph theory, and there are algebraic objects like power series or polynomials that count patterns. However, what is an appropriate notion of power series in this case? We don't know. So to summarize, our equivalence up to same number of walks is done the following way. First, we have graph-to-graph transductions, let's say T1, T2, and then they are composed with this graph-to-power series transduction. Now, what can be done is work on the MSO part and maybe find an MSO transduction that differentiates outputted graphs even more. Maybe there isn't transduction, and it's a question, is there such a transduction that maps non-isomorphic graphs to graphs with different numbers of walks, and therefore differentiates them so much that even our formal power series, which was not enough, then would be enough to differentiate the graphs. And also, as already mentioned, maybe we can work on the algebraic side and find a power series or something else that can distinguish tree-width k graphs, maybe even a special case of trees, or maybe a problem which on the first glance is not a special case of our problem, because it's about cyclic words that are words identified up to cyclic shift. However, they can be encoded as graphs, which is not described on the slide, and this is also an interesting problem. Are MSO transductions graph to cyclic word? Can they be tested for equivalence? It is important that those algebraic objects have to be compatible with composition of output objects, because this is how they will be constructed. Once the graphs, for example, are composed, the counterpart, the corresponding power series should also be composed at the same time. This is everything I wanted to say, so thank you for your attention.